So back to this the discussion we were having. So we have one relationship between L2, the length of the plastically deformed region, and sigma 0. I want to derive another relationship because then I'll be able to calculate L2. And so this other relationship will be derived by considering only this interface region between tablet 1 and the mortar. We have a few regions here. We have the region that the tablet has failed, like here and here. We have a region that the tablet has deformed plastically, so shear stress is constant in those regions. And we have a region that the tablet has deformed plastically. We said the length of this region is L2 and the length of this region is L1. And because of symmetry, this is also L2. Now, this tablet 1 is in equilibrium, which means the total force, and the equilibrium equation that I told you earlier, like d sigma dx is equal to tau f over d sigma 1 dx is equal to tau f over b, is the differential form of the equation, the differential form of the equilibrium. But we can also look at it as the integral form. And for instance, we can say sigma 0, the total force applied to the right is sigma 0. This has to be balanced by the sum of the forces applied by the mortar to the brick. So the force applied by this guy is sigma 0 times b, which is here. The force applied by the shear is this integral. I break it from O to A, from A to from O to A, from A to B, and from B to C. And I have symmetry. So it's going to be 2 times from O to A, because one is here, the other one is here. I have 2 times from A to B, that's the plastic region. One is here, the other one is here. And we have the elastic region, which is here. Although it's symmetric, but we just consider it into one integral. Now, the first integral is 0 because there's no shear stress in the failed region. The second part is an easy integral because the shear stress is always tau if it's constant. And so let's move forward. Let's calculate each of them and see what we get. So the first one is 0. The second one is just tau f times L2. The length is L2, and the shear stress is tau f. Now, for the elastic region, it's a very interesting problem, but it's a problem that we have already addressed. Let me just make that case for you. Imagine this is tablet 1, and this is tablet 2. Now, also imagine that a region in between here is the region that the tablets have deformed elastically. So this is elastically. So basically, it means that this distance from here to here is actually L1. Oops, sorry. Is actually L1. Now, at this very end of the elastic region, I hope you know that the shear stress is exactly tau f, because that's the boundary between elastic and plastic region. So in some sense, you remember the first part of the problem where we looked at the elastic deformation? The length, the force carried out by this region, only by this region of the elastically deformed is exactly the same as the force carried by a pair of tablets that are deforming elastically, have the length of L1, but the boundary has reached the critical value. So the force is so high that the boundaries have failed. In the first case that we solved, L was a constant. In this case, L1 is a variable, but the basic principles and the equations we use to solve remains exactly the same. So if we replace L with L1, L in the first part of the problem, which was elastic, with L1, we should get exactly the same equation. So basically, this is what we had from the past. If I just replace L with L1, I'm done. And it still is tau f because the boundaries are reaching tau f. And so that's kind of a interesting remark when we were driving these equations. That was a relief when we convinced ourselves that this is a logical statement. So then our previous equation will become this, flat and simple. So this is that integral. This equation didn't come from any universe other than the one we live in, and that was this integral of tau dx. This is the plastic region, this is the elastic region, and the failed region is here and is not here because it's +0. That's for the failed region. I just wanted to clarify that. So, and by the way, this value here, oops, let me clarify this. This is equation 16. Please modify that in your notes. So, combining equation 15, which was the previous equation we had for L2, with this new equation 17 that we derived for L2, allows us to calculate L2 as a function of L1, basically get a relationship between L2 and L1. At the same time, I can combine this integral equation with this, I can combine this equation with the integral equation, which is this guy, and that allows me to calculate the load-bearing capacity of this guy as a function of the length of the elastic region. So basically, this equation, you input in it the length of the, you input in it the magnitude of the sigma 0, and it tells you how much of the region is remaining elastic. Now, the interesting part for us to consider is that as you increase sigma 0, the plastic region grows and the elastic region has to become smaller and smaller, okay? And now if you basically, so if you go back to equation 18 and you let L1 equal to 0, you obtain the case for the length of the completely grown plastic region. So basically, as you can see from this equation, when I am applying when I'm increasing the load in the material, L1 will keep going down and L2 will keep going up. the length of the plastic region keeps growing and growing. So then I can calculate from equation 18 a limit for the length of the plastic region. So I am going to stop this video here and then continue in the next video.